Hi everyone, welcome to the Nuvoton Level 1 training. I'm Abby, Field Application Engineer of Nuvoton. Today, I'm going to introduce the ADC function of our NuMicro M031 and M032 series. In this section, we'll tell you what ADC is, how to convert ADC, what features and functions it has. We'll also go through the block diagram to let you know better about ADC. ADC stands for Analog to Digital Converter. It can convert an analog signal into a digital signal. In the world of integrated circuit, the signals are divided into either 0 or 1, which means low or high in electronics. However, in the real world, the signals are analog, like battery voltage. Therefore, we have to use ADC to convert such analog signals into digital signals to show the level of it. By the converter, we could connect analog world with digital world. We can then present analog information in the digital world. We can take this graph for example. This is an analog signal. How do we convert this analog signal to a digital signal? The way is to sample the value of the analog signal every a period of time. Like the second graph, we sampled it about 10 times to get the digital signal. The third graph is the converted result. Compare the first graph and the third graph. You may notice that if you sample it more frequently, the result digital signal will be closer to the original analog signal. If you sample it less frequently, the result digital signal may be distorted. Therefore, the frequency to sample it is very important when we are doing analog to digital conversion. By the example above, you could know that the frequency to sample an analog signal is important. It is one of the parameters of ADC. We call it a sampling rate, which means how often to convert input analog signal. As we mentioned before, the higher sampling rate, the more continuous digital signal it would be. Another parameter we would like to mention is the resolution. Resolution means the bit length of digital value for the conversion range. It also means how detailed we divide the conversion range. When more bits are used for the conversion range, the measuring quantity would be smaller and contains more details. Take the scale on the right-hand side, for example. The red scale has bigger quantity, and the blue scale has smaller quantity. If we have battery level ranged from 0 to 5 volts to measure, the result will be different by which scale we use. When we use the red scale, which the quantity is bigger and the resolution is lower, we can only get a value roughly, like 3 volts. When we use the blue scale, which the quantity is smaller and the resolution is higher, we can get a more accurate value, like 3.5 volts. Therefore, the higher resolution, the more accurate digital signal it would be. To ADC, sampling rate and resolution are two important parameters. Sampling rate means how often the data will be sampled. Resolution means how detailed the data will be presented. Speaking of how to convert, in microcontroller, a very commonly used ADC architecture is SAR ADC. SAR ADC is Successive Approximation Register ADC. It works on binary search method. Let's see how it works by below example. In this example, it is a 10-bit ADC, which means the resolution bit length is 10 bits. If the analog value we are going to convert is the battery voltage range from 0 to 5 volts, 10 bits resolution means we divide 0 to 5 volts into 2 to the 10th power quantities, which means 1024 quantities. Let's go through this example by input voltage 3.6 volts. First of all, since the range is from 0 to 5 volts, we take the middle value 2.5 volts to do the comparison. Compare 2.5 volts and the input 3.6 volts. 3.6 volts is bigger than 2.5 volts. Therefore, the first bit would be filled with 1. By the comparison, we know that input value is ranged from 2.5 volts to 5 volts. And then we continue the comparison to narrow it down. take the middle value between 2.5 volts and 5 volts, which is 3.75 volts, to do the comparison. Since 3.6 volts is smaller than 3.75 volts, the second bit would be filled with 0. Following the rule to fill all the bits, the result would be 101110001 in the end. 101110001 is 737 in decimal. 737 means the level of the voltage by this 10-bit resolution. We could get the input voltage by dividing 737 by 1024 and multiply by 5 volts. The result is 3.5986 volts, which is very approaching to 3.6 volts. It is how we convert from analog to digital. Now, we are going to show you what ADC features we have for NuMicro M031 and M032 series. First, the ADC is a 12-bit SAR ADC with 10-bit accuracy guaranteed. Second, we'll talk about the analog input voltage range. AVDD is the power supply for internal analog circuit. VREF is ADC reference voltage input, which means the upper bound voltage value defined for ADC. VREF should be smaller than AVDD. It means that we can define the upper bound voltage value by setting VREF. For example, if you know that the voltage to be measured won't exceed 2.5 volts, you may set VREF as 2.5 volts to utilize the resolution better. Therefore, the analog input voltage to be measured would be ranged from 0 to VREF if VREF is defined. Else, the input voltage would be ranged from 0 to AVDD. In addition, the AVDD is from 1.8 volts to 3.6 volts. The input channel could be 16 single-end analog input channels or 8 fully differential analog input channels. The differential channels can be used for a comparator. Also, the sampling rate is up to 2 million SPS, which means 2 million sample times per second. Furthermore, our ADC has below features. For each channel, each conversion result will be stored in a data register. For example, if there are 16 channels, there will be 16 data registers for storing each conversion result. ADC supports extend sample time function. We can set it to have extend sample time from 0 to 255 ADC clock. Some analog circuits may have higher input impedance. Higher input impedance takes longer to charge up the capacitor. Therefore, ADC could handle such situation by extending the sample time. By extending the sample time, it will have more time to charge the capacitor, and then ADC could get more accurate value. ADC also supports internal input source like bandgap voltage. There is a built-in bandgap voltage value in the chip. It could be used to calculate the supply voltage when AVDD is connected to the power supply. ADC supports to generate the interrupt when the counter value is matched in compare mode. In addition, ADC supports PDMA function for accessing the conversion data via direct memory access. Here is the clock source of ADC. The clock source of ADC could be either 48 MHz HIRC, PCLK, PLL fault, or 4 to 24 MHz HXT. You can choose the clock source by setting ADC SEL register. After choosing the clock source, there is a frequency divider, ADC DIV, for you to set whether to lower down the frequency or not. Besides, you have to enable ADC clock by setting ADC CKEN register. ADC clock will start to work after it is set and enabled. This is the block diagram of ADC. First, these are the control registers of ADC. From the lower left corner, we can see ADC channels and VREF. they are all connected to pins outside the integrated circuit. Like we have talked about before, VRAP will connect to a voltage less than a VDD. There is a capacitor in sample and hold. When we want to measure voltage from an ADC channel, like from ADC channel 0, the switch in sample and hold will be turned on, and channel 0 will start to charge the capacitor. When it has been charged for a period, the switch will be turned off. Then the voltage in the capacitor would be the input voltage. The input voltage then will be measured by successive approximations register ADC by the way we have mentioned before and store the value in an according register. For example, the value measured from ADC channel 0 will be stored in AD data register 0. Every sampling will also trigger an ADC interrupt to notify the change. The value could also be accessed by PDMA request. The sampling could be triggered by STADC pin, PWM, or timer. Besides, it could also be triggered by software by writing 1 to ADST pin. Here, we are going to tell you the setting of ADC input channel. First of all, the ADC input pins share with GPIO. Therefore, if we need to use ADC, we have to configure GPIO as input mode. Setting GPIO as input mode will keep it staying at floating state. Therefore, it won't affect the actual voltage we want to measure from analog circuit. Besides, we have to disable digital input path as well. This is for avoiding the current leakage. It will make the sampling more accurate. In addition, there are two input modes for ADC input channel. One is single-end input mode. The other is differential input mode. When the single-end input mode is chosen, the input voltage is the value measured from each channel. When the differential input mode is chosen, the input voltage would be the difference between V plus and V minus. However, how to set GPIO and ADC pin? Here is the example code for it. We use the function GPIO set mode with the parameter GPIO mode input to set GPIO as input mode. The first line of the code would set GPIO PP0 as input mode. The second line is to configure PP0 as the pin for ADC input channel 0. Besides, don't forget to disable the digital input path of PP0. It could be simply made by calling the function GPIO disable digital path. After above are all done, we can start to use ADC input channel 0. After configuring ADC pin and channel, ADC module can be powered on by below function ADC power on. Furthermore, we also provide below features for our ADC. We have 4 ADC operation modes, which are single mode, burst mode, single cycle scan mode, and continuous scan mode. In addition, an analog to digital conversion can be triggered by these 4 ways. It can be triggered by software writing 1 to ADST register. It can be triggered by the external pin STADC. It can be triggered by timer. It can also be triggered by PWM. There are 4 kinds of interrupt sources in ADC. EDF flag will be set once an ADC operation is completed. CMPF0 and CMPF1 are flags related to ADC comparators. Such flags will be set when conditions are matched. CALIF1 is a flag that will be set by calibration mode when condition is matched. When either flag is set, if interrupt is enabled, an ADC interrupt will be triggered. We're going to introduce the 4 operation modes in order. First, let's check out the single mode. Single mode means that analog to digital conversion will be performed only once on the specified single channel. If there are more than one channel enabled under single mode, it will always choose the channel with the smallest number to do the conversion. the other channels will all be ignored. For example, if channel 4, channel 5, and channel 9 are all enabled, only channel 4 will do the conversion when it is under single mode. Channel 5 and channel 9 will be ignored. We can see from below graph, when ADST is written to 1, it will trigger the sampling and conversion once. After the conversion is finished, the ADF bit will be set to 1. If interrupt is enabled, the ADC interrupt will be asserted. The ADST bit remains 1 during the conversion. When the conversion ends, the ADST bit is automatically cleared to 0, and the analog to digital converter enters idle state. Usually, the conversion time will take 17 ADC clock time. However, in this example, since there is an extra extended sampling time for 2 ADC clock time, the total sampling and conversion time would be 19 ADC clock time. In burst mode, analog to digital converter samples and converts the specified single channel for 8 times and sequentially stores the result into FIFO. Check below graph about the operations. When the ADST bit is set to 1, analog to digital conversion is started on the enabled channel with the smallest number. Notice that if software enables more than one channel in burst mode, only the channel with the smallest number is converted. Other enabled channels will be ignored. When analog to digital conversion for the specified channel is completed, the result is sequentially transferred to FIFO and can be accessed only from ADDR0, the ADC data register 0. When there are more than or equal to 4 samples in FIFO, the ADF bit will be set to 1. If interrupt is enabled, an ADC interrupt will be triggered. VALIDF, the valid flag, will be set to 1 when there is valid data in ADDR0. User can read ADDR0 repeatedly until VALIDF turns to 0. The conversion will keep going until ADST is cleared to 0. Single cycle scan mode will scan all enabled channels once. ADC will sample and convert each channel in sequence from the smallest channel number to the largest channel number. Take below graph for example. There are 4 channels enabled in this example. They are channel 0, channel 2, channel 3, and channel 7. When the ADST bit is set to 1, analog to digital conversion starts. It will scan by the order, channel 0, channel 2, channel 3, channel 7. Each result will be stored in according registers. Like channel 0 result will be stored in ADDR0. Channel 2 result will be stored in ADDR2, etc. When the conversions of all the enabled channels are completed, the ADF bit will be set to 1. If the ADC interrupt function is enabled, the ADC interrupt occurs. After ADC finishes one cycle conversion, the ADST bit is automatically cleared to 0, and the analog to digital converter enters idle state. Continuous scan mode works the same way as single cycle scan mode. The only difference is that it will continuously do it until software clears ADST. When analog to digital converter completes the conversions of all enabled channels sequentially, the ADF bit will be set to 1. If the ADC interrupt function is enabled, the ADC interrupt occurs. The conversion of the enabled channels with the smallest number will start again if software does not clear the ADST bit. Therefore, before ADST is cleared, it will keep sampling and converting all channels in sequential order. After introducing the 4 operation modes, we're going to show you how to enable ADC channel and set operation mode. Below function, ADC open, is used to make it. The second parameter, input mode, is used to specify the input mode of ADC channel. The third parameter, OP mode, is used to specify the operation mode. The last parameter, CH mask, is used to specify which channels will be enabled. By the example, channel 0 is enabled as single-end input mode, and the ADC operation mode is specified as single mode. We have mentioned before that we can extend the sampling time by setting extend sampling time. By the extend sampling time, the channel will have more time to charge the capacitor. The maximum extend sampling time is 255 ADC clock. Extend sampling time could be set by below function, ADC set extend sample time. The module number means which ADC to be set. For example, 0 means to set ADC 0. By the example, it will set extend sample time of ADC 0 to 2 ADC clock time. We have also mentioned that ADC can be triggered by software. However, how to trigger ADC by software? We can use ADC start CONV to make it. By calling this function, ADST bit will be set to 1 and then trigger analog to digital conversion. After conversion, we can use ADC get conversion data function to read conversion data from registers. By the example, it will get the conversion result of channel 0. Above is the introduction of ADC. Thanks for watching. You could subscribe our channel for more information. Besides, please do not hesitate to contact us if you have any question.